Today we're going to continue in our series of lectures on duality. What I'm first going to do is I'm going to talk about some more examples of just computing duals for specific things so you can get used to the kind of math that we're doing here. And then what we're going to do is we're going to talk about different interpretations of duality, and I will also introduce formally the idea of strong duality. Okay? So I want to start with, remember our setup where we have min over x, f naught of x, subject to constraints, fi of x less than or equal to 0, hi of x equal to 0. This is our general optimization setup, right? And what is this called? This is the primal, right? And for this, what we did last time was we then computed a Lagrangian, which is L of x comma lambda comma nu. The lambdas are constrained to be greater than or equal to 0. And we said that this is basically a way of incorporating the constraints themselves into the objective function, right? And we argued why basically the Lagrangian incentivizes the function, or incentivizes the optimizer, to satisfy the constraints, right? We had this kind of hard thresholding where we would set, if you violated the constraint, you would send the value off to infinity. And the Lagrangian's kind of a soft way of dealing with that. Everyone remember we kind of talked about that last time? And then from there, we kind of derived the dual, right? Which was, well, this g function, which is the minimum of the Lagrangians over x, right? That gives a lower bound always, is what we proved. And we said that, well, of all of these, I want to find the best lower bound. And that's going to be given by this g of lambda and nu. And I'm going to maximize that, right? So I had the minimization became a maximization problem. And what was the special property of g that we discussed? G is always a concave function, right? So what that means is that this problem of the dual, what is special about the problem of the dual? It's always a concave maximization, which means it's a convex problem, right? And it's the kind of problem that we like to solve. Everyone remember this general setup from last time? Okay, good. So now let's consider another specific example. Let's say P star okay? So let's look at this optimization problem. It's a minimization problem, again, over x. What type of objective function is it? What's the nature of this? It's a quadratic, right? You've seen this before. What is the constraint? What is this xi square equal to 1? Let's say I equal to 1, 2, all the way up to n. Let's say these are n length vectors. What does that constrain xi to be equal to? What are the possible values it can take? 1 or minus 1, right? There are only two values. Is this a convex problem? In general, this is not a convex problem, right? Is this constraint convex? Nope. Is the objective function convex? Are all quadratic functions convex functions? What does it depend on? W. Under what conditions is this x transpose wx convex? If it was PSD, then it would be convex, right? But in general, we don't know that. All we know is W is a symmetric matrix. So it could be positive semi-definite, or it could have some negative eigenvalues. We don't know, right? So in general, this is not a convex problem. The last time, we did the example of the minimum norm problem, right? that was a convex problem, right? Our constraint was just a linear constraint, and our objective function was a very nice convex quadratic function, right? This is now not a convex function, so I want to try and show you that duality applies not just for convex things, right? It applies for non-convex things as well. Okay, so now just to make sure that you all attended class last time, find the dual of this. So let's work on it together. This problem is in general called the partitioning problem, and you can probably see why, right? You have a bunch of elements, x1, x2, all the way up to xn, and what you're trying to do is you're trying to assign each of them a value, either +1 or -1, right? So depending on whether you're positive or negative, you're basically in one group. And what this W matrix is telling you is what is the cost of having an xi and an xj in the same group, right? Because what this is doing is basically a sum of sigma wij xi xj, right? And so you're trying to partition these things into two groups such that you minimize the cost, okay? So this is a problem that comes up frequently in lots of kind of computer science types of applications. So when we solve this, do we have any inequality constraints here? So what is our Lagrangian going to look like? It's going to look like x comma nu, right? There is no lambda term here because there are no inequality constraints. And what is this going to be equal to? People call it out because I want to know that everyone's with me. So not just the first row. First row is great. You guys talk. But I want to make sure that everyone, the entire class is with me. So what's the first term here? Plus. How do you want to write it? So what is this constraint here? How do you write this constraint? How do you want to rewrite this constraint? You want to write this as hi equal to 0, right? Why am I getting blank stares? Like, are you already all done? Yes? No, then what's hard about writing the next thing here? Tell me what's hard, because if you don't tell me what's hard, I cannot help you. If you tell me what's hard, I might be able to help you. If it's easy, you've done it. If it's hard, you're telling me why. You know how to do it? Okay, tell me then. Speak up.
I mean, you want a 0 on the right-hand side.
Okay. So what do I write here?
So xi squared.
Okay, xi squared.
-1.
-1, and what do I put here?
8. Yeah, no.
And is this all I need to write, or
No.
what do I need? To write a sum I going from 1 to n. Right? I'm just rewriting this constraint to be equal to 0. Okay. So here I have a bunch of these terms. I can just rewrite this to be in the following form, right? I can write this as x transpose w. And if I look at these terms, nu I xi squared, can I write this as a matrix vector product? What if I consider x transpose nu1, nu2, nu_n? Does this give me exactly kind of this first part of this term here? Right? So I'm going to write this as w plus the diagonal matrix of the new vector, x, plus now, or maybe minus, sigma nu I. Okay, that just allows me to pull all of my x's together, because the next step I want to do is I want to minimize over the x's, right? So all I've done is kind of pulled all the terms with an x all together in my Lagrangian. Now what I want to do is I want to minimize over x of L of comma nu. And let's look at this term now. So I have x transpose some matrix times x, okay? And I'm going to try to make this as small as possible, okay? What are the possible values this thing can take? What's the smallest value I could make this thing? This first term. Can I make this minus 100? Maybe, maybe not. Under what condition could I make this equal to minus 100? So if this matrix has a negative eigenvalue, let's say this matrix, is this a symmetric matrix? This is a symmetric matrix, right? So now, can I make this as small as I want if it has a negative eigenvalue? Right? If I have a negative eigenvalue, I just choose x to be in the direction of the eigenvector corresponding to that, and I'm going to send it off to negative infinity, right? So when I'm minimizing over x, I can always choose x to be in the direction of that eigenvector. And then if I have a minus infinity here, does it matter what these n's are? No, right? No matter what they are, they're still finite. And so I'm going to get a minus infinity, right? So what is the min over x of this term? What did we just discuss? Yes? What is the minimum value of x transpose ax over x if a has a negative eigenvalue? We've done this now many times, right? We did it as a Rayleigh coefficient. We did it in the context of the SVD. No, if I want to try and make this, so that's when you're constraining x to be a unit vector. So if I have, let's say, so okay. Are there multiple people confused about this? Okay, I'll ask me in office hours then. I think that everyone else is on board, so I'll, okay. If there's anyone else confused about why this is the minimum of this is minus infinity, raise your hand. Okay, I see 3 people raising their hands. Okay, that's not enough for me to go over it again. Come to me in office hours. This is choose x is equal to some alpha times the eigenvector corresponding to lambda min, and then take alpha to negative infinity, or lambda negative, right, really. Any negative eigenvalue, and this will do the job. Okay, so I have this equal to minus infinity. And for this, what is the condition under which this will hold? Okay, so if w plus diagonal nu I, or nu, is not PSD, right? Another way of saying it has at least one negative eigenvalue is saying it's not PSD. Okay? So what if it was PSD? If it was PSD, then what can I say about x transpose times this matrix times x? It's always greater than or equal to 0, right? The smallest value this can ever take is 0. And so if I'm minimizing this over x, I'm going to try to make this thing equal to 0. And I'm going to try to make this thing, it is just what it is, right? I don't have any choice over it. I only have choice over x. The n's are constant in this case. So I'm going to make this 0, and so what is this thing going to be equal to? It's going to be negative sum of the nu i's. If is PSD. Everyone with me here? Good question. So you're saying that what happens if this is positive definite, not positive semi-definite. If this is positive definite, that means I am still, so in the case that it's positive definite, I won't necessarily be able to set this thing to be equal to 0, but I can always, the lower bound that I'm going to get is still going to hold. So in that sense, I'm going to always have this be greater than or equal to here. No, we don't need to worry about infimums and supremums here. Yeah, I don't think it's worth bringing those in. Okay? If I take x equals 0, oh, that's true. I could do that. Yeah. Good point. Sorry. Okay, sorry. Good question. I didn't give you a good answer. Even if this is positive definite, I can always choose x equal to 0. And that would still give me this. So I don't actually need to do this. Sorry. This is exactly equal. My bad. Yes?
Don't we have a constraint that the xi squared have to equal 1?
Don't we have a constraint that the xi squares equals 1? Okay, great question. So what are we doing here? We're looking at the minimum of the Lagrangian. The whole point of getting to the Lagrangian is that now we get to do an unconstrained minimization. Right? We have incorporated the constraint into the Lagrangian. And so now we're searching over all possible x's. Okay? This constraint has already been built in. Does that make sense to everyone? So here, this minimization, when I write this min of L of x comma nu, I'm not writing any constraints here. Okay? This is important that everyone realize this. This constraint is not binding to us here anymore. Okay, good. So now we have this. Now what's the next step in finding the dual? Yes? Could we maximize the sum of the news? Exactly, right? So we want to say now, I know that this minimization, what do we call this function? What is the name that we give this particular function? This is g of nu, right? And so now we know that every single one of these g of nu's is a lower bound for our optimum, for our primal problem. So we want to find the best lower bound, right? So we want to find So I'm trying to find this best lower bound, and I get to choose my nu now, right? Nu is under my control fully. That is what I'm going to use. There are two different cases for this nu, right? Either g of nu is equal to negative infinity, and that's in the case where w plus diagonal of this nu is not PSD, or this thing is PSD, okay? I want to maximize g of nu. Which case do you want to be in? Do you want to be in the case where you're always resigned to be negative infinity? If you want to maximize your function, do you ever want to be negative infinity? No, that's a disaster, right? That's like the worst maximization you could ever get. So remember, you get to choose nu. So can you choose nu to make sure that this constraint holds? Right? So when I'm maximizing now my g of nu, I'm going to say I'm going to choose nu to make sure that my g of nu is never negative infinity. Okay? And so when I write this, instead of writing these two cases, what I'm going to write is I'm going to say that this is the same as maximizing subject to the constraint that w Okay? So what I've done now is I've said that let me try to avoid the bad case, and I'm going to rewrite my problem by adding this constraint. The last time when we did this, our dual came up unconstrained, right? But this time, we're saying, instead of writing this or this and having some complicated g function, I'm just going to add this as a constraint, which makes me have a nicer, cleaner formulation. Okay? This is something that is typically commonly done. You will often find that when you're finding the dual of something, you will have some case in which your function goes to negative infinity. And you will want to kind of ignore that, and you will condition, and you will add a condition to your dual problem to make sure that that negative infinity doesn't occur. Make sense to everyone? So this is now your dual. What do we know about this function? We know that this is now a convex problem, right? This had better be concave. We know that that's true just by our very, by the fact that it's a dual of a primal. So we know that. But this is still not an easy problem to solve, okay? We cannot easily solve this and get exactly what we want. So what are we going to try and do? We're going to try and find some values of this dual that will allow us to give bounds, okay? So I want to maximize this thing, right? I want to maximize the negative of the news. That means I want to make the news as small as I possibly can, right? I want to maximize the minus of something. That means I want to make the thing itself small, right? So how small can I possibly choose new? Can I choose nu to be minus infinity? Probably not, right? What is constraining my choice of nu? This thing, right? So now, what is the smallest nu I can choose that still makes sure that this constraint is satisfied? You could choose 0. 0 is one option. Could you do better? Depends on W, right? So what if I told you that, yeah, go ahead.
Maybe you could choose nu to be the equivalent to like the smallest eigenvalue of W or inverse of that, like additive.
Right, exactly. So now I have W, and W is symmetric, right? W is basically something like U transpose lambda U, right? And it has all the eigenvalues along this, along the diagonal of this matrix, okay? So now this is now, by adding this, I'm basically shifting the eigenvalues, right? This is just, by doing this, I can say W plus diagonal nu is equal to U transpose lambda U plus U transpose or I could write, here I am. Okay? And so now what I want to say when I want to, if I choose these diagonals, right? If I choose this diagonal nu such that every single one of these entries is equal to negative lambda min. Okay? Then I can write this as U transpose lambda U plus U transpose minus lambda min U, right? Which is equal to U transpose times this thing here times U. And what is going to be true of all of the entries along the diagonal here? They're all going to be greater than or equal to 0, right? because what you have here is really lambda max all the way to lambda min, right? And so these are just going to get subtracted from each other. And so what I'm going to get here is everything greater than or equal to 0, right? The smallest entry is necessarily going to be 0. Everyone see that? So by choosing now all of the nu I is equal to negative lambda min, I'm ensuring my constraint is satisfied, but I'm still beating kind of choosing the nu's as 0, right? As someone had pointed out, this depends on w. So basically choose the nu i's to be the negative of whatever the minimum eigenvalue of w is. Okay? And that's going to give you, we're not proving that this is necessarily the best you can do, right? So now if I wanted to prove that this was the best I could do, I had to come up with an argument that says that I can never exceed this, right? I'm maximizing this, so I'm saying that, look, here's a value it attains. Now I want to say I can never go beyond that. We don't have an argument like that. So all we have is that this is some lower bound for our primal problem. Okay, and so what is the corresponding lower bound? I have n of these. So n times lambda min of w is the bound that I get, right? And so I get basically that my p star is always greater than or equal to n times lambda min of w. I don't know exactly what p star will be, but I know that at a minimum, this is the cost I'm going to pay. And what this gives me is that now suppose I come up with some partitioning, right? Like I'm trying to divide you all into teams, red teams and blue teams. Then I get a baseline by which I can compare my implementation, right? Maybe my implementation is great, maybe my implementation is not great. But this gives me some baseline that gives me a sense of, how much better could I possibly do. So here I have if nu I, choose nu I equal to negative lambda min. Yes?
To the question, why don't we choose the mu I according to the lambda i's?
Why don't we choose the nu i's according to the...
Mu1 equals to negative lambda max, and w plus the diagonal mu vector will still be a solution.
So the reason we cannot choose individually is that we don't know this u transpose. We don't know this transformation, right? So I'm not, this only works when I choose all of the elements on the diagonal to be exactly the same. I can't do this when I have different elements on the diagonal. So here, if I put diagonal nu I, if I have something where every element is the same, I have nu I, nu 1, nu 1, nu 1. This is, I could write this as u transpose and u, just like this, right? Because now I can have matrices commute. Because this is diagonal with all of the elements being exactly the same. It's like multiplying by a scalar. Could you explain how you made the new dual problem from... Okay, so why is this the dual? Okay. So are you with me till here? Okay. So now this g is basically, I have a g function, and I have g is equal to, or g of nu is equal to minus infinity in case A, and is equal to something, I don't know, 10 in case B. Okay? You're trying to now maximize g. Which case do you prefer? You prefer the second case, right? So now I can always write my maximization of g. This is over an unconstrained nu, right? So when this is over an unconstrained nu, I have two cases. Well, nu is either in case A or in case B. Am I ever going to choose a nu that puts me into case A? No. So it is equivalent for me to write this as max over nu belonging to case B g of nu. Right? Because I know that case A forces me to negative infinity. I will never choose a nu that makes that happen. It's not going to be in my interest in maximization. How do I know that here in this case, we do not have strong duality. I do not know that P star is equal to D star. All I know that this is a lower bound. So that's why I've written P star is greater than or equal to n lambda min. I don't know that it's equal. We don't have a proof for that. Is there a way to prove that this is the best you can do? Not that I know of. It's an open problem. So if the question is, what if W had some positive and some negative eigenvalues? As soon as you have even one negative eigenvalue, you can always drive to negative infinity. So anything with a negative eigenvalue always falls into case A. You're never going to consider it, because you're minimizing. The minimizer will always take you to negative infinity.
I guess instead of setting all the Wi's to negative lambda min, can't you set some of them to...
No, you cannot, because then you cannot have this bounding work. You cannot set them to be separate values, because otherwise you cannot get this, you cannot guarantee this condition. Everyone, this is the same question I've answered 3 times. Can you not get a better lower bound by setting nu I is equal to negative lambda I? No, you cannot, because if I do that, I cannot guarantee that W plus diagonal nu I is positive semi-definite. When I have a diagonal matrix like that, I cannot do the trick that I just did here and decompose it that way, because I do not know that the symmetric, these are 2 symmetric matrices, but I do not know that the bases that are in their SVD or in their spectral theorem are identical. So this trick does not work if I had different lambda i's along the diagonal. Why is the best lower bound equal to the max of g? So we answered this last time. The best lower bound, so every single g of nu is always a lower bound, right? We've proved this. For every value of nu, g of nu gives you a nu lower bound. Nu equal to nu lower bound, right? Remember? So which nu do you pick? You pick the nu that maximizes it. Okay? Other questions? Okay, good. So here, again, to emphasize, we do not know the optimum value for this problem, right? But the nice thing is that we can get a lower bound, which allows us to still kind of get a sense of how things are behaving. Okay? Good. Okay, so the next thing I want to do is I want to introduce you to a different perspective on duality. We've been thinking about duality in this one particular way, and now I want to introduce you to a different perspective. And that's the kind of min-max perspective on duality. Okay? And for this, first I have to prove a theorem for you. This is the min-max theorem, and this says theorem. Max comes first. Make sure I'm writing this correctly. Yes. So what this theorem is saying is that if I have some function that is a function of two variables, x and y, okay? And I have, what I'm doing is I'm minimizing this function over x, but I'm maximizing it over y. Okay, so the two different variables are trying to do two different things. Then the min max is always larger than the max min. Okay? It's always better to, I mean, depending on what you're trying to do, I'll give you another interpretation of this later, but right now the best easiest way to remember is min max is always greater than max min. Talk about a game theoretic interpretation of this in just a minute. Okay? So why is this theorem true? Do you want to take a minute actually to try to do it on your own? Okay, take a minute to try to do it on your own before we go into it together. Okay, that's my 1 minute timer for you guys to have time to try it on your own. So let's come back to think about this theorem together. Okay? So this is a lot going on in this theorem, and the best way I find to think about this is to just think about it piece by piece. We're going to first just prove it algebraically and convince ourselves that it's true, and then go and think about interpretations of this and why it's relevant to what we're doing. Okay? But first, I just want to convince you that this thing is true. So how are we going to prove this? Well, we're going to say that here we're looking at some minimization over all x's and maximization over all y's. There's a lot going on, right? And our approach is going to be to say, let's fix some x and some y and kind of use some baseline as a comparison. Okay, so what I'm going to say is fix some x naught belonging to x, y naught belonging to y. Okay? And then I'm going to define this function h of y naught, okay, which is going to be the min over all x belonging to x of the function x, y naught. So in saying, let's look at the function of interest, okay? Fix a y naught, right? Let's not worry about the maximization over y. Let's just fix something. And let's consider only the minimization over x's, okay? Let's just define that function to be some h of y naught. Okay? You can see clearly, depending on y naught, this is going to have a different value, right? So therefore, this is a function of y naught. It's not just some one value. There's, based on different y naughts I choose, this is going to do a different thing. Yeah? And why am I choosing to minimize over x's? Because I know that my x wants to make things small, right? So I'm choosing to minimize this over x, not maximize, because in both cases I'm always minimizing over x. And then on the flip side, I'm going to define g of x naught. And I'm going to do the same thing, f. I'm going to fix now x naught. And I have a y. And now am I going to minimize this or maximize this here? Maximize this, right? So for a fixed x naught, how good can I do by varying my y's? Okay? Okay, so now I have my h of y naught, which is equal to my min over x belonging to x of f of x comma y naught. So this is this thing. What am I? Min over x of f of x comma y naught. Okay? So I'm looking at all of the x's and choosing the smallest one. If I picked a specific x, is the f of that going to be larger or smaller? If I, instead of having this minimization, I said just pick one specific value. It's going to be, like, the minimum has to be smaller than any specific value, right? So this is necessarily less than or equal to f of x naught comma y naught, right? X naught is some specific value, right? Okay. How could I make this even bigger? Now let's say I fixed x naught. If I wanted to make this bigger, I could say instead of y naught, choose the best y, right? So I could say this is the max over y belonging to y, f of x naught comma y, right? Okay, which is just equal to my g of x naught. Okay? So I have proved that h of x naught, or sorry, h of y naught is always less than or equal to g of x naught. Right? Just this chain of inequalities argues that. And did I have any specific, is there anything special about x naught and y naught? No, right? So for every x naught, y naught, I have h of y naught is less than or equal to g of x naught. Now can you make progress? I have two things. This is true for every y naught. This is true for every x naught. If I wanted to milk this inequality for all it was worth, the less than or equal to side, do you want to make it bigger or smaller? I want to make this side bigger and the other side smaller, right? I want to make this big and this small. That gives me the tightest possible inequality. So what can you do? Take 1 second, quick, think. Inequalities are always the most interesting when the gap between the kind of the less than and the greater than sides are as small as they possibly can, right? So for example, Cauchy-Schwarz, probably the first inequality you've learned about. It's interesting because it has an equality condition, right? There's a case in which you can make the two sides equal, right? When the two vectors are exactly aligned, Cauchy-Schwarz gives you an equality, right? And in other cases, it's an inequality. So that's kind of an example of an inequality that can be made tight. So if you want to do the same thing here, right? You want to minimize that gap. What do you want to do to this side? Maximize. So if I'm going to maximize over now y naught belonging to y, h of y naught, right? I get to choose y naught. So I can always choose the y naught that makes h the biggest, right? No one stops me from doing that. I get to choose any one. This is still less than or equal to. I similarly get to choose any x naught I want. So I pick the one that makes that value the smallest. And which one is that? Right? This is true. But just rewriting this now, what is the definition of h of y naught? You can just plug it in. right? Which gives me exactly what I want. Does it matter that I have an x naught and a y naught here? These are just dummy variables, right? Like, I basically have proved I can just as well relabel these to be x and y, and I get exactly the result that I wanted. Okay? So this is a very kind of brute force way to prove this, right? Like, I'm showing you a technique by which to prove this, but it's not giving you a lot of necessarily intuition about what's going on or why this is true. But do you see that this is true now? Believe me, everyone? Okay. So now, why do we care? Turns out that this inequality is the heart of weak duality. It's exactly another way of seeing what we saw yesterday, or last lecture, but in a slightly different format. Okay? So connecting back to what we've been thinking about, we have P star is equal to min of f naught of x, right? Such that fi of x is less than or equal to 0, and hi of x is equal to 0, right? This is our primal problem. Okay? Everyone remembers this? And then we wrote the Lagrangian. Is equal to so what if I just, when we're computing the dual, we then say we proceed to minimize this over x, right? We say let's compute the minimum of this over x. Instead, I'm just going to say let's consider the max over lambda greater than or equal to 0 and mu for this quantity. I'm not sure I'm following your question, but let me answer a related question, which is, what does it mean to have a maximization and a minimization of a function which has multiple variables in it? So basically, this is almost exactly what we mean. So if I have some function that is a function of two variables, so if I have f of x comma y is, let's say, x squared plus y squared, right? This is a function of two variables now. And when I'm saying I want to maximize this over all x's, okay, whatever I'm going to get is still going to be a function of y, because there's still a y remaining there. Okay? I can then maximize it over both x and y, or I could say I want to maximize it over x and minimize it over y, or I can do any combination of the above. But if I only optimize over one variable, what remains is a function of the other variable. So I could maximize this over x, but I still, it's still dependent on what y I choose. Okay, coming back to where we were here. So to remind everyone, we said we have our primal, and I wrote out our Lagrangian. And I want to, just as an exercise, have you consider the maximization of this Lagrangian over lambda and nu. Okay? So what is this going to be equal to? So let's say we had an x that was completely feasible, right? That satisfied all of our constraints. If x was feasible, what does that mean about fi of x? Less than or equal to 0, right? And hi of x are all exactly equal to 0. So when x is feasible, this term doesn't even show up. Okay? This term is always negative. Right? fi's of x are always negative. So if I knew that fi of x is always negative, and I'm trying to maximize over lambda, what's the lambda that I'm going to choose if fi is negative? I'm always going to choose 0, right? So what is the maximum over lambda and nu of this entire quantity when x is feasible? This is exactly equal to f naught of x if x satisfies constraints of the primal, right? What about if x did not satisfy the constraint? Okay? Let's say x satisfied all the equality constraints, but it violated one of the inequality constraints. Okay? So f1 of x was strictly positive. If f1 of x was strictly positive, okay? Everyone follow me here because you're going to get lost otherwise. If f1 of x was strictly positive, and I'm trying to now maximize over lambda, what lambda would I choose? f1 is positive. I'm trying to maximize this whole thing. Lambda I can choose to be any positive real, any non-negative real number. What lambda am I going to choose? I'm trying to maximize. I'm going to choose lambda equal to infinity, right? Okay, so what is the maximum value I can have for this if f1 of x was greater than 0? Infinity, okay? So f1 of x is just one example. If any of the inequality constraints are violated, what can I do? What is the maximum I can drive this to? I can always drive this to infinity, right? Okay? If any inequality constraint is violated. Now let's consider, let's say all of the inequality constraints are fine. They're satisfied. But you choose an x such that the equality constraint is violated. So you find something such that, let's say h1 of x is not equal to 0. It might be positive, it might be negative. Let's say h1 of x is strictly greater than 0. What are you going to choose nu1 to be to maximize this thing? Again, infinity, right? If h1 of x is strictly less than 0, what are you going to choose it to, nu1 to be? Negative infinity, right? So remember you were asking me why does lambda have constraints, but nu doesn't have constraints? Right? This is why. Okay? So it's just not, this is not true if any inequality constraint, but if any constraint is violated, I can always make this go to infinity, right? So yeah, hold tight. So basically, what are we doing here? This is a little bit of an exercise, right? We haven't yet understood why we want to maximize this with respect to lambda and nu. We're just saying if we were to maximize this with respect to lambda and nu, we have these two cases, right? Okay? So what I want to do now is, can I use this to write P star in some alternative format? So in this case of the dual here, when we were trying to maximize something, we always ignored the case, person with the question. So when we were in the case where you were trying to compute the dual over here, right? And we were trying to maximize the g, and the g had two cases. And in one case, it was negative infinity, and in the other case, it was something finite. If we're trying to maximize something, we always hate the value negative infinity, right? Similarly, if we're trying to minimize something, what is the value we always hate? Infinity, right? So now, can I rewrite my P star? Okay. as, I'm trying to minimize over x maximum over lambda greater than 0 mu of L of x lambda and mu. What is this thing? This thing inside here, we just argued, is that this thing is either equal to infinity or it's the primal given the constraints, right? If x is violating the constraints, it's going to infinity. If x is in the constraints, then it's exactly equal to my objective function f0. So am I ever going to choose an x that violates the constraints? Nope, right? So I can rewrite my primal as exactly this by this argument, right? It's a min-max. Have you been thinking about min-maxes? We know this is now, by our theorem, greater than or equal to max min of same function okay? But what is this thing on the other side? How did we define our dual? Right? What we said was, well, let's have our Lagrangian. And we said, oh, the minimum of this we defined as g of lambda comma nu. And then we maximize that g over lambda and nu. So what is this thing exactly equal to? It's exactly our dual. Right? So we argued in a different way last time. We said that p star is always greater than or equal to d star. We proved that by showing that basically we have a stack of lower bounds. We're choosing the best lower bound. A new gives a new lower bound. So we tried to find the best one. And we said that the best of those is always going to be a lower bound on p star. But all this is it's an instantiation of the more general min-max inequality that we're applying to our special case of the primal dual problem. Okay? Does everyone see that? Everyone with me? Okay, good. So now you see why this is kind of relevant to us. Why do we care, right? Okay, good. So now what I want to tell you is how does this connect to some sense to game theory? Any questions about this so far? Sorry, before I move on. I have not written any constraints here. Look in this minimax inequality. We have incorporated, by using the Lagrangian, we are incorporating the constraints into the formulation of the primal and the dual. Right? Note that this maximization of the Lagrangian, why is this equal to p star? This is equal to p star because this maximization goes to infinity every time you choose an infeasible x. There is no implicit x feasible here. This is any x. This is really important. That is why this is powerful. Or there's many reasons it's powerful. That's one of the reasons it's powerful. I'm not writing x feasible. There's no constraints here. The only constraint here is lambda greater than 0. It's really important that you observe this. Everyone with me? Thumbs up? Okay, good. Why can we solve the dual problem but not? We can't necessarily always solve the dual problem either. All we know that it's always a convex problem. So we don't necessarily always, we're not like, you can find the dual of something and that doesn't mean you can solve it. But you can use it for interpretations in many ways, and there's going to be so much in the rest of the class where you're going to see how the dual is useful. If your primal was convex, would you ever care about finding the dual? Yes, many times convex problems are still hard to solve, and the dual can still be useful, and you'll see lots of examples. There's going to be lots and lots of homework. So no shortage. Okay, good. So, there was a question here, how does this connect to zero-sum games? Okay? So let's say you're playing a game, okay? And you have player A and player B. Okay? Player A gets to choose X. Player B gets to choose Y. And then there's a payment f of x comma y from A to B. Okay? So I choose X, you choose Y, and then we decide that based on that we evaluate f of x comma y, and then I pay you whatever f of x comma y is. Okay, everyone understand the game? So my incentive is to minimize f of x comma y, right? I don't want to give you any money. Your incentive is to maximize f of x comma y. You want to take all my money, right? Good. Intuitively, do you want to go first or second? Second kind of feels better, right? You already know what I'm going to do, so it's probably better for you to go second. Okay, so let's try to understand this. Let's see what happens. Okay, so let's say A goes first. Okay, A goes first and chooses x naught. So now the number of things that are in play are basically f of x naught comma y, right? X naught is now fixed. A has chosen x naught. Now it's B's turn. B wants to maximize the thing. So what is B going to choose if x naught is fixed? Which y are you going to choose? The maximizing y, right? You're going to choose so when I'm deciding my strategy, right, when I'm choosing my x naught, I know that whichever x naught I choose, this is the y you're going to choose, right? Does everyone see that? So now how should I choose my x naught knowing that this is how you will respond? I should choose the x naught that minimizes the payoff, right? So I should choose min if I'm playing first. Because I know you're going to play after that, and I know this is what you're going to do. Because I know you're going to maximize. All information is public. So second player sees, when I choose x naught, you know that I've chosen x naught. Okay. What if B goes first? If B goes first, and let's say it chooses y naught, then what am I going to do? Right? I have f of x comma y naught is now fixed. Y naught is pegged. So now what I'm going to do is I'm going to choose the min x, right, for this thing. And therefore, knowing that I'm going to minimize, how are you going to choose your y naught first move? You're going to choose your y naught first move in a way that kind of maximizes this quantity, right? Because you know I'm going to try to minimize it afterwards. Okay? And now, which one of these is bigger? Right? The min-max is always bigger than the max-min. Min-max is bigger than the max-min. So if I go first, I end up paying more. If I go second, I pay less. So I always prefer to go second, because then I've already seen your move. Right? intuitively, you already, before we even saw any of this, you argued that the second player knows more stuff. It's better to go second, right? So this is a zero-sum game in the sense that the total amount of money being exchanged, my loss is your gain, your loss is my gain. The total amount of money that we make as a collective is the same. It's always zero. There's no external money being poured in. That's why it's called a zero-sum game. And so you can interpret duality also as a game between the primal variables and the dual variables, right? The primal is trying to minimize. The dual is trying to maximize, okay? And there's this kind of trade-off tension that's happening. And intuitively, where this is coming from is that same intuition that you all had without doing any math, that, oh, the second player is probably better off if they already see the first player's move. Now, this is not always true, right? Like, for example, there's sometimes where it's better to go first. First mover's advantage is a thing. This is a specific case in this special case of a zero-sum game. In this particular setup where going second is better. There are games where it's possible that first mover has an advantage. But this particular setup, this is what we're talking about. OK, that's it for today. See you next class.